You're good. If you ever need to do it later. All right. Hello, everyone. Guy's going to give a quick announcement of the review. Then I'll give more announcements. Then we'll do our review. It'll be quick.
Good morning, everyone. So I promise last time on the semester I'm going to be here. Also, because it's the last day of class. But we have final exam review. It's going to be on Monday, December 1st at 11:30 a.m. in the student meeting. You don't need to remember all that because if you go to your web courses right now and go to the physics SART SI/peer tutoring course you have on the web courses, you should find all the information in one of the announcements. The problem set has already been posted, so if you want to work like ahead and have questions during the exam review, that's fine. The exam will be recorded and posted, and the answer key will also be posted. However, that doesn't depend on me. So they might post at the end of the day, so you won't have much time between the end of the exam review and your actual final here. So if I were you, I would totally recommend, I totally recommend you guys to come to the review on Monday, 11:30 a.m. So check the announcement, check the problem set on the link that is posted there, and yeah, it's another great resource for you to file. Thank you.
Thanks. All right, y'all. Most important piece of information at this point is the final. I think I've said it now like 10 times or something, but that's how you make people remember it. A week from today is our final. It starts at 10, not 10:30. I know our class meets at 10:30. Our final is at 10. Why? Because UCF has to schedule these things. Our final is next week, Tuesday, December 2nd, 10 to 12:50. Make sure you come prepared. What does that mean? Calculator, pencil, good night rest, all that kind of jazz.
If we come like a couple minutes late, is that going to be
If you come a couple minutes late, no, it will not be a problem. Basically, what's going to happen is if you come late, you'll just have half class time. Yeah. Correct. It is in this room. Our exam is in this room. We will be packed in like sardines. I'll make some quick announcements in the beginning. One of them will be like, don't cheat, it's not worth it, classic things like that. I won't regale you with that speech now, but you will not need a Scantron. It's going to be like every test before this with Scantrons on the back page. There is no free response. It is going to be 36 multiple choice questions. I know I said 40, but I ended up reducing it very slightly just to make the mental fatigue a bit less. I have also, again, I made a draft of the test. I've sent it out to a couple people to look at. I myself went through the test and wrote out things, and it took me about 23 minutes to do the test. I'm not saying that as a brag. I made the test. It should go quickly. I should know how to solve every problem that I wrote. Every problem on that test is a problem I wrote. So of course I'm going to do it quickly. But that 23 minutes means that is the time it takes. That if you can look at a problem, read it. If you know exactly what to do, that is kind of the fastest you can do the test carefully. Again, I actually wrote out things and all that. I read through all the problems. That's also why I checked for typos. I wrote out what I felt I needed to write out. So, with that in mind, you all have more than 6 times that amount of time, 6 to 8. You all will have time to think about every single problem on this test. About 6 of the problems are involved. When I say involved, that's the question I get. So you like 6 of the questions here have kind of giving you the free response that we've done in the past. So there will be some problems on there that will take a little bit to write out. Nothing crazy. I'm not expecting you to spend 10 minutes on like those problems. But there is some of those problems on there. But you will have time. In my opinion, if you know what you're doing, if you study and done well and all that stuff, time should not be any concern whatsoever. Which will be super important because I have a test 10 minutes above. After this FPRO's exam ends, I have 10 minutes to get to my next exam. And that's actually probably for the benefit. Some of you are in the same situation where you have another exam that might be soon after. So when the test ends, it ends, and we will vacate the premise quickly.
explain that like non-physics like courses like assessment thing?
Oh, yeah, thank you. I didn't know you mentioned that. There was a separate web course where you go to the pre and post test. It results in giving an extra 1% extra credit to your final grade in class. I haven't gotten that Excel file yet, so if you did those surveys, sometime next week I should get that information, and all I do is I then go through Matchsticks and add that grade to it. So if you want to include that in your grade calculations, use my Excel spreadsheet and then add it. But yes, that is if you did both. The pre and the post, each is worth 0.5%. So together it's 1% total. Yeah.
So, like 69%, it shows up in the C.
Yeah, so you might have seen this at this point. I round up. So your grades get rounded up. So in this class, a 90 or above is an A. I round every single one of your grades to the highest whole number above it. So if you have an 89.01, that will round to a 90, which is an A. Now, if you have an 89 flat, it does not round. You can be like, oh, it's so close. That's always going to be the case. There will always be some grade that is so close. And so I'm already giving a bit extra by rounding up no matter what. But just be prepared for that. Whatever your grade will be after the exam will be the grade. At this point, there's no way to make up anything. There's no way to redo anything. It'll be what it is. And there's some freedom in that. That once you're done, you're done. But I know that can cause some stresses. But yeah, that's just how that goes. Yeah.
The survey between the pre-test and post-test?
I mean, the pre and post test is in separate web courses from our course entirely.
Okay.
Yes, not the surveys. Okay. The other thing I want to point out is I've made all the study resources that I was going to make are made at this point. So in the final, so I'm done making files. In the finals, so if you go to the web courses and you go to the final, there's a folder called Final. In that folder is the review that we're going to do today, which is very brief on electromagnetic waves, and then I'll kind of ping to test one review and spend a bit of time on that. I also have every single clicker question in a couple of PowerPoints. I have it in the order, so the order that I've taught it to you, and I have it mixed up. If it's not mixed enough, I did the mixing before this class in about 5 minutes. If it's not mixed up enough, mix it up more. But there you go. It's all there. So, with that in mind, we're going to do this electromagnetic wave stuff. It's going to be pretty straightforward. Just a summary of what we did the last week and a half or so. And then we'll look at test 1. Honestly, we might look at test 2, but we'll see time-wise. If we don't get to test 2, hopefully it's not a big deal considering we did it like 3 weeks ago. Wasn't too long ago that we did that exact review. So, electromagnetic waves is what we spent the last little bit on. You all do have a quiz that is due, I forget the exact day that I set it to. It due the day of the final? Yeah, I made it due the day of the final on purpose because the quiz is useless to you after the final. You should do it before the final. So you all do have one more assignment to do. The recitations are done. You haven't realized that? The last due date was this last Saturday. The electromagnetic waves is due, and I made it at midnight for some weird reason, but whatever. The day of the final at midnight. Do it before the final. It's not very useful to you after the final. You would rather realize you don't know how to do these things before than on the test itself. Remember the purpose of these quizzes. So don't forget there is one more quiz, and then that's it. So electromagnetic waves. I got kind of 3 summary slides. I think it's 3, maybe 4. And then a couple of problems. Nothing crazy. Remember, there's features of a wave. We have velocity. These waves move. They have a frequency. Frequency is how many times a full wave happens every second. Wavelength is how the distance between 2 identical parts of a wave, crest to crest, trough to trough, middle to middle. We've seen that. These are just kind of definitions when it comes to periodic motion. Not just waves, but all periodic motion. Period is the time it takes for one full cycle. Notice I didn't say the word wave because this applies to more than just waves. And the angular frequency is instead of regular frequency, which is how many cycles per second, this is how many radians per second. It's another phrase for angular frequency is angular velocity. It's how much angle changes every second. Just like regular velocity is how much your distance changes every second. So great. Definitions. Yay. These are things that if you don't know what any of these, if any one of these you don't know, you should know what these mean. These are vocab words you all need to be familiar with. And that's outside of this class, you should know what these words mean. Every single one of you, regardless of your major. These are just like periodic motion's really important. Computer science, all that jazz. All right. Then we have the general wave function. This is the one on the formula sheet. So it says that some wave, it's you plug in an x value and a t value, it tells you the y value, which would be like how up down the wave is. And so it's the amplitude, that's what A stands for, times sine, and then inside the sine you have 2 pi over lambda x minus plus vt. I'll remind you all the reason it's minus or plus. In fact, I'll type it out here. The minus plus means if minus, wave travels to the right. If plus, wave travels to the left. It's the opposite. That's why it's minus plus, to show you it's the opposite. Whatever it says, it's the opposite of that. X is where I want to measure it, lambda is the wavelength, v is how fast it's moving, phase shift. I'm not going to test you on it, but I thought it's important. Again, just so you realize, at time equals 0 is this wave. So normally, when sine is 0, you should get 0. But if there's a phase shift, then it's not 0. You know, it's shifted. The phase is how much a wave is shifted.
Are you ever going to give us a wave function where it's like x of something or z of something?
Yeah, that's a good question. Am I ever going to give you a wave function where it's something other than y? No. It's nothing great. All this means is that the wave is traveling in the x direction, and we're measuring how tall it is y. I'm not going to try to mix things up by putting different stuff there. Now, I say that there is the electromagnetic waves where we replace y with e and things like that, but yeah, we tend to just put them in the x direction, and I'm just going to keep doing that because I don't want to trip you all up on that. But yeah, it is important to realize that which way is this wave moving? It's not moving in the y direction, it's moving in the x direction. How do you know it's moving in the x direction? Just draw this picture. If you drew this, what this thing looked like, y is how up down it is, x is, and if you like drew this wave, you know, it's going to be traveling in the x direction. You can hopefully see that with this picture. This wave would go outside. All right. So great. And then we made them electromagnetic waves. How do we do that? We replace the amplitude with the electric field is E. Its magnetic field is B. Everything else is the same with one small exception. The velocity is the speed of light because that's how fast light travels. That's the only difference. This one is not on the formula sheet because the other one's on the formula sheet and they're the same thing. The only thing that changes is B becomes C. So great, that's just what we did. Neither of these are the formula sheet, the one before this was. The next two equations are on the formula sheet. This is the relationship between the electric field and magnetic field. Specifically, these are the amplitudes. If you take the amplitude of the electric field and you take the amplitude of the magnetic field, you divide those two, you get the speed of light. That is the relationship between them. They are coupled. If I doubled the electric field amplitude, then the magnetic field would also double. C is a constant. C does not change. So whatever happens to one of these things, the other one will increase or decrease by the same amount, so you always get C. Now, this can technically actually be any point in time. The electric field at any point in time divided by the magnetic field at the exact same time spits out C. But we just pick amplitude to make it easy. All right, and then we have average intensity. And intensity was something we talked about that's good for you all to speak. Again, this is something that's just good to know. It's useful to measure the energy delivered by light in this way. How much energy per second per meter squared? This last weekend, I built a fire with my nieces and things like that. This is a useful thing for you all to think about this season if you build a fire. Why? Fires, you might not realize this, emit most of their energy is light. Something to think about when you're sitting around the fire, you can tell people around it fun facts. How do you know it's emitting most energy by light? When you're sitting in front of the fire, just put your hand in front of your face, and your face will be colder. You didn't block the air, you blocked the light. What part of your body is hotter when you stand in front of a fire? The front part. Not because the air is that different between the front and the back, it's because the front's facing the light. Why am I saying this? As you get farther from the fire, the intensity of the light is going to actually change because it's going to be delivered, the energy is going to get spread out. No one knows. You stay farther away from your Fire, you're gonna get less energy per second. Sorry, I believe the intensity stays the same. The power changes. Intensity stays the same regardless of where you are. Let me actually fact check. I don't want to be tripping over myself. But as you get farther away, it gets weaker. The bigger you are, the more energy you're going to capture. I captured more energy than my nieces who are like 3 or 4 years old because they're smaller. Not surprising things. All right. It is related to the magnitude of the fields. There it is. This is the equation on the formula sheet. If I give you we're going to see a problem. We'll just do it. So, great. So this problem is kind of everything I need you to be able to do.
Sorry, those two ways, one goes in the Y, one goes in the Z direction.
Yeah, that's a good, because the electric, yes, one of them moves in the Y. This is always a pain in the butt to draw. The electric field wiggles up and down. The magnetic field is horizontal, is perpendicular to that. So yes, that's why, yes, you are completely correct. I'm not going to test you on that directionality stuff because we didn't have enough time. I didn't give you enough problems on it. We didn't have the time for it, but it is important to realize they're perpendicular to each other.
When the EZ direction is like positive, does that mean it's going to go with the negative Z direction? Or?
Yeah, so in the case of this wave, if they were minus, it goes x minus CT, if you're traveling in the positive x direction. Both of them would be the electric field and the magnetic field. Yeah. And the electric field would be in the y direction, and the magnetic field would be in the z direction, and they're perpendicular to each other, and they would. So one goes up, the other goes left, right. One electric field goes up, down, magnetic field goes left, right, kind of, sort of. All right. So this problem has kind of all the pieces, all the things you need to be able to do. So it says some electromagnetic wave has a wavelength of 600 nanometers and peak magnetic field strength of 7 times 10 to the minus 6 Tesla, and it travels in the x direction, the positive x direction. What is the equation for the electric field for this wave? What is the average intensity of this wave? How much energy per second would a person receive if they are 1.5 meter tall and 0.3 meters wide at the point where we measured this field? Yes, it's easier. You're approximately a rectangle. Pick your favorite, rectangle, oval. Ovals are too complicated. All right. Try it out. I'll give you all a couple minutes. See if you can make this wave equation. This is something you definitely need to be able to do by next week.
So B is the magnetic field and E is the electric field.
Yeah, the E one makes sense. The B one, unfortunately, is not in, but it is. Remember the process. First thing we identify is what I'm even solving for. Always start there. Don't just, what am I even trying to find? Write that down. That's how you avoid mistakes. If you don't write that down, you'll likely make a mistake.
Capital E.
We are finding the equation for capital E.
Yeah, like E equals.
E as a function of x comma t.
Right. It's only cosine, right?
Not cos. We tend to use sine. It doesn't really matter though. So you're trying to build. So this is, you all are trying to build the equation. You are not solving for a number for part A.
Wait, if it's a magnetic field, wouldn't it be B?
It would if I was solving for B. That's a great point. Yeah, that's why you always want to write down what you're solving for, because that's going to help you catch some things. So the question I got is a really good question. In the problem I don't give you the electric field strength, I give you the magnetic field strength. What you going to do with that? There's something you have to do with that information.
Wait, is magnetic field strength B naught?
Oh, yeah, no, magnetic.
It's B naught.
field Is the electric field divided
B
by
naught. Magnetic field is B, electric field is E. Yep. All right, so first we write down what we're solving for. And then, I'm going to write, there's only one equation for this, so that's probably the one we're going to use. And when I say equation, this is the general form. If we know the general form, we can just take what we have and make it fit into this. Technically, there's a phase angle, but we're going to ignore it. The phase angle won't matter. We're actually just not going to even bother with the phase angle. We're going to say it's 0. If I don't mention, again, I keep telling you this phase angle thing. If I don't mention it, no problem. Don't worry about it. That's the rule of thumb. I have to explicitly say the phase angle is this. How much it shifted? All the chest. All right. So if y'all look at this equation, we just kind of read it from left to right. Oh, I need the electric field amplitude. Do I have the electric field amplitude? No. How could I find the electric field amplitude given what I have? Let's look at what I do have. I have wavelength, and I have B naught. That's it. Great. How do I do it? How do I go from the things I have to the things I want? Yep, remember C equals E naught over B naught. Simple rearranging. E naught equals C B naught. This is the benefit of writing things down and writing what we're solving for, because I can guarantee you many people probably just took this number. If I just kind of gave this and I didn't say anything, it's very easy to take this magnetic field and just chuck it in the front. And that just comes down to, if you write stuff out, that's how you avoid making those, I'm going to call them simple mistakes. So this is therefore going to equal, let's calculate it. 3E8 times 7E minus 6. Normally I say always use a calculator, but these problems are kind of nice. 3 times 7 is 21. E to the 8, e to the minus 6, that's just going to be e to the 2. 8 plus negative 6 is positive 2. So, great. And the units for electric field, you can either do volts per meter or you can do newtons per coulomb. Both are units for electric field if you want to write it down. All right, so 21 E2 times sine. I actually made this problem maybe even too easy for you all. We just put lambda in there. Make sure you all know your unit conversions. Make sure you all know your unit conversions. On the multiple choice, I didn't really bite too many people in the butt, but on the first response, I saw people make a lot of mistakes with unit conversions. Make sure you all know the basic ones. Kilo, centa, milli, nano, and micro are the ones that we've used in this class. That's the ones you all need to know. You need to know, how to go from kilo. So like if I just pick meters as my base unit, you need to go from kilometers to meters, centimeters to meters, millimeters to meters, micrometers to meters, nanometers to meters. Those are all the base. Those are like the most common. I'm not going to give you anything other than those. No deci, no hecto. No. Shouldn't be any mega. No, there's no mega on the test. Mega is 10 to the 6. It's a nice one, but it's not going to show up on the test.
So it'd be nice to just know the scientific notation for each of those.
100%. So this would be 3e3 meters. This one would be 3e to the minus 2 meters. This one's going to be 3e to the minus 3 meters. This is a skill every single one of you better be able to do. I made up a number. You're right. I don't know why I picked 3. Let's make them all 3. 3e to the minus 6, and this one's 3e to the minus 9. If you're going backwards, which you tend not to do, you would just flip the sign. Okay, this one's going to be x. We're going in the positive direction, so it's minus ct, and that's it. That's the answer. That's the equation for it.
What if you wanted us to like distribute it all?
Then do it. Yeah, if all the answers have it distributed, then distribute it. Yeah. A variation on this problem I could say is instead of giving you the wavelength, I could have given you the frequency. I could have said, hey, it has a frequency of this. Fill the equation. How do you do that? Wavelength and frequency are related by C equals F times lambda. Specifically, on the formula sheet, it's V equals F times lambda. Light travels the speed of light, so C equals F times lambda. So if I give you frequency, it's really easy to get wavelength with that equation that's on the formula sheet. So they're inversely proportional. All right, so great. Make sure you can do that. I promise you there's 3 questions on the test where basically if you cannot read this wave function, you can't do that, you won't get those questions right.
So that's going to be fine.
Yeah, let me put.
Wait. Oh, are you done with his question?
Not part B and C.
Oh, no. I was asking, are you done with his question?
Oh, yeah, go ahead.
So like the minus and plus CT, isn't that correlated to the Z?
It's correlated to the direction you're going. Minus means you're moving in the positive x direction. Positive means you're moving in the negative x direction.
Right, I'm just confused on like which axis.
If it's a function of x, it's traveling in the x.
Yep.
All right, so moving on to part B. What is the average intensity of this wave? So we're going to take the things that I wrote because they're going to be useful. And you'll have so many options here. I'm just going to steal this. So for part B, it says find the intensity. So part B, we want the average intensity. It's always average. We tend to not care about peak intensity too much. No, at least I'm not going to ask you any questions with that. Okay, how do I find the average intensity? There is only one equation on the formula sheet with average intensity, so it's probably that one. Power average over area equals E naught B naught over 2 mu naught. If you're like, where did I get that? Oh, look, here it is. Okay, so if you want average intensity, do one of these things. Either take the average power and divide it by the area, or to the intensity of the fields divided by 2 mu naught. Now, in this case, we have E naught and B naught, so we can just plug those in. However, in the one that I wrote down here, I didn't have both, just to show you all that you can do this. Remember that C equals E naught over B naught. So you could do B naught equals E naught over C. And if you wanted to, in this problem we don't really need to, but you could take this and put it here. And so this does equal E naught squared over 2C mu naught. Make sure you can do that, because what if I don't give you both fields? What if I only gave you one of them? What are you going to do? Algebra. You're going to do algebra.
Isn't there those 2 other forms that you showed last week?
Yeah, there's a couple forms of it. There's one purely in the E, there's one purely in the B, there's one with both. On the formula sheet, I gave you one with both. So either derive both or put it on your note card. All right, so pick your favorite. I'm just going to pick the one that I derived because it has every number I need right here on the front. So 21e2 divided by 2 times 3e8 times 4 pi e to the minus 7. You do not need to have mu naught memorized at this point, but honestly, if you haven't memorized it by this point, you probably haven't done enough problems. Speed of light. Yeah. Thank you. I should square the numerator. Good catch. On the test, I do not make answers that happen by like common math mistakes. I do try to put answers that would happen if you make a physics mistake. So like if you're solving for electric field due to a point charge and you forget to square the bottom, that means you solve for voltage. It wasn't like you just made a math mistake. You literally solved for a wrong variable. It would be voltage. So there is stuff like that.
Wait, isn't there 2 different D's? Like there's like a D with like a squiggly kind of stuff?
A what?
Like
Oh, that's epsilon naught. That's a whole different thing. Yeah, that's a constant. 5,848. Yeah, we'll round up. So this is my intensity. And the units for intensity are energy per second. That's measured in watts per area, which is mu squared. Great, yay! There's part B done. Part C said find the power average that someone would feel if they were in this light. And so how do we do that? Oh look, it's there's only one equation with it. I average equals power average over area. So the power average is going to equal I average times area, and my area is just going to be the length and width of the person because they're a rectangle, because I said so. So this is a pretty easy problem. 1.5 and 0.3 are the numbers. 1.5, 0.3. These are numbers based on myself, roughly. I'm roughly 1 meters tall. If I put my arms to my side, I'm roughly that wide. All right, and that equals 26,320 watts, which is not safe, but yeah, that's way too much. That would burn me very quick. That way too much energy per second.
Oh, length times width.
Yeah, because it's a rectangle person.
It was given to us?
Yep. Yeah, for part C, I said, make them a rectangle. There's how tall they are, wide they are. Yeah. Yeah, I collected them wrong. I think you did. You got a smaller number? If I multiply 6,000 times the number is bigger. Oh, wait. You might be right. I might have put 3. You're right. Thank you. I was reading those numbers and I was like, they're all bigger than 1. Yeah. Thank you. Good news. 2,632. I was off by an order of magnitude because I accidentally put 3 instead of 0.3. It's still a lot, not quite as spicy. 26,000 is a lot. Perspective, a light bulb outputs about 10 watts, 20 watts of light. This is more. Okay, so every mistake I made is a good reminder that those are the easy mistakes to make. Missing a decimal place, forgetting to square something. How do you avoid making those mistakes? 1, you go slowly. 2, you double check that the equation matches what you wrote down. And the last one is to make sure that what you typed in your calculator matches what you wrote down as well. This is why I've said it a few times now. Ideally, you should only plug the numbers into your calculator one time. You build a function, you type the entire thing in one time. That lets you compare the one thing that you wrote down to the one thing you typed. That is the best recommendation I can give for avoiding mistakes. That's been based on my experience of doing a lot of problems. The more times you type things in your calculator, the easier it is to hit the wrong button. Also, the harder it is to check your work. So, all right, cool. Reflection and refraction, this is where it gets super trivial, super quick, super easy. I'm not going to even ask for a question on reflection, but I put it here because you should know how light reflects. It's so simple, it's so basic, you should know it. Light bounces with the same angle and hits rhythm. I'm not going to test you on this. It acts like a bouncy ball. That's a useful thing for all of you to know. Refraction, I am going to have questions on. Light travels at different speeds in different materials, quote unquote. The index of refraction gives us that ratio. You can never go faster than the speed of light. So n will always be bigger than 1 because c is the biggest number. B will always be smaller. Take a number, divide it by a smaller number, you get a bigger number. The smallest n can be is 1. You cannot be smaller than 1. All right, and then why is this useful? It tells us how light bends when it goes from one material to another. This is incredibly useful. Glasses, contacts, lenses, like anytime you want to manipulate light, you need to be familiar with this. Another great application of this is when you all look at a road and it's really hot and the air looks all wavy. Why? Because hot air has a different index of refraction than cold air, so it bends the light. Anytime you're all seeing light and it's doing things that look weird, it's almost guaranteed to be because of this equation. That it bends when it goes from one material to another, and that's what makes different things. Rainbows, that's why you get rainbows. That's why you get wavy air. That's why you can tell where gas is when you have a gas leak and the air looks all wavy. Why? Because gas has a different index of refraction than air, so it bends the light. That's a great question. Is that why asphalt becomes a mirror when it becomes really hot? I'm actually not 100% on that. That's a great question. I have to think about more. It might be because there's a really hot surface of air there that it's doing some weird things. But I have to double check that. That might be total internal reflection, but I'm not sure. All right, so this problem is super quick, super easy. I'm just going to kind of knock it out real quick. And this is and then we'll do a quick overview of test 1. This is the review for everything we just covered. Light travels at 1.7, e to the 8. smaller than 3 to even 8. Yay, we got great for laws of physics. What is the index of refraction? All right, first step, what am I solving for? N. How do I solve for N? N equals C over V. Great. Then we do it. 3E8 divided by 1.7E8. I cannot do 3 divided by 1.7 in my head. I'll get a calculator for that. And the E8s cancel and I get 1.76. No units, done. And that's it. That's the index of refraction. It is 1.76 lower. There's no units because the units cancel. C is speed, V is speed. They both have units in meters per second. They cancel. Great. If light starts in air, what angle does the light need to hit this material at? So its angle of refraction, not reflection, refraction, is 70 degrees. Something I put in the last slide, but I didn't say that loud. Whenever we talk about these angles, they're measured with respect to the area vector. So we draw that dotted line. The solid line is the surface. So we're going to start in air. We're going to end in material. I don't know what it is. I made up this whole problem this morning. Who knows what this material is? Glass is about 1.5. Water is about 1.3. So this is something that's, might be more dense than glass by a little bit. Okay, so the angle of refraction is 70. So this angle is 70. Not the angle I go in with. The angle of refraction is the angle that the inside of the material. Okay, so the question is, what's the one up here going to be? And that's going to be some bigger angle. Why do I know that? Because when you go from less to more, the angle bends towards the normal. I've just done enough of these problems to know that. I'm solving for this angle, incident angle. So I'm solving for theta incident. We might call it theta 1 if you wanted to. So N1 sine theta 1 equals N2 sine theta 2. 1 is where I start, 2 is where I end. It's that easy. So if I rearrange this equation, I'm going to do the algebra super quick here. Theta 1 is going to equal sine inverse of N2 sine theta 2 over N1. I just did a bunch of algebra in a couple quick step. Make sure you're cool with that. Remember, rule of thumb, you only want to plug in your calculator one time. So we get sine inverse of 1.76 times sine of 70 divided by 1. And I'm going to hope that this, I didn't give you a problem that was not solvable. There is a chance that the angle I picked is not actually solvable. Yep, it's undefined. Yay. Pick an angle smaller than 70 for me. 62. Way smaller.
42.
42. All right. If I was in the ballpark of 70, it still probably wasn't going to work. All right, so I got to redraw my picture. Don't worry, on the test, I'm going to make sure that the answers are possible.
Just have undefined as an option.
I could have undefined as an option, that'd be me. Nope, this one's still undefined.
How about
12.
We'll just keep making angles. Yay, we did it. 12. All right, great. So if this is 12, not 120. We get the angle is 21.46. The reason that some of these angles are not possible is because the light will only bend so much. There is a maximum angle it will refract with. We can figure out what that maximum angle width is if we put this at 90. Well, 89.999999. You need to pick something that's not quite 90 because it'll just spit out 0. Yeah. So, great, done, easy. Make sure you can do these. They're pretty straightforward. If you've ever taken a physics class, you've probably done these problems. If not, now you have. Hopefully. Okay. So, at this point, I'm going to do a quick survey. I'm not going to actually solve any more problems. I'm going to do a quick survey of all the things that we've done in this class and remind you what you need to know. That's kind of the rest of this class. This was a summary of the last things I taught. I now need to make sure that you all remember what's important from previous test 1, test 2. Because test 1 was a hot minute. You know, it was like 10 weeks ago or something. Not quite, something like that. All right, so I'm going to refer to test 1 review. That's available for you. Remember, another great study resource is the tests themselves. Those are posted in test 1 folder. There's test 1 and test 2 folder. There's test 2. You know, make sure you can do those. Where is my review? Typo on where?
I saw a file with typos.
Oh, that was the file I made during the test to show you all what the typos were. Yeah, that's what I made on the spot. All right. Hopefully this has the writing on it. Okay, so test 1. It's been a hot minute. I'm going to go through this quick. Just remind you of the things you need to know. Charges, they exist. Protons, electrons. Protons are positive, electrons are negative. A trend throughout all of this is we pretty much define what a proton would do. What's an electron going to do? The exact opposite. Your intuition is probably going to tell you what a proton does. What does an electron therefore do? The opposite. Yeah. Yeah. I'm just going to zip through it and tell you the main things. Remember how to get net charge? The net charge with any neutral object is 0. Doesn't mean it has no protons and electrons. No, it does. This table is made of protons and electrons. I just have an equal number of both. What determines whether I have charge is whether I have more of one versus the other. If it's positive, more protons. If it's negative, more electrons. We can only really transfer electrons easily. You can technically transfer protons, but it's a little tricky. Great. Coulomb's law. There's the equation. Remember that the formula sheet is a fantastic way to make sure you remember all the things in this course. So throughout these reviews, it's just a bunch of equations. If you don't recognize these equations or you do not know what they are used for, then you should find problems related to it. You should practice this. 2 charges experience a force. Positives, like charges repel, opposites attract. It's over r squared. Be careful on that r squared. That's a classic mistake. This is force. The force between 2 things. This was experimentally observed. K is 99. Nice number. Yes, that's on the formula sheet as well. This is a vector. You got to break it into components. Don't forget about that. Yay. All right. Math. What makes this force? We made up something called fields. Are they real? Are they not? Light is a pretty good argument that they're real, considering we say light is the fields themselves and nothing else. This field makes a force. One charge makes a field. The other charge experiences the field and experiences a force. So E equals F over Q. Find the force on the charge divided by the charge itself. Boom, you got the field at that location. You do not need... So remember, a charge makes a field everywhere, even if nothing is there. Even if nothing is there, there will be a field there. When does that field do something? When I put a charge at that point. All right, fields point away from positives and towards the negatives. Remember that kind of matches your intuition? Fields point away from positives. That sounds kind of natural. Negative. Electron can do the opposite. A field is kq over r squared because one charge makes a field. Everyone. Now, this is the one that I did your free response on. Do not forget how to do the integrals. This is something you need to know how to do. This is something you need to know how to do. Don't forget how to build the integrals and do that kind of thing. Inside a conductor, the electric field is 0. Alright, here's the reminder for how you set up the integrals. This is a skill. You will need to be able to use calculus. It is a tool in your toolbox. If you do not know how to use it, someone who does will get the job. You need to know how to do calculus. You need to know what it's representing. You need to know how to build integrals. You're going to keep seeing it in your future classes. Maybe not computer science majors, but engineering majors, you should. If not, that's disappointing. All right. Great. Step by step. Make sure you can do it. There's problems where we did that. Make sure you can do it. On the test, there was one of these. Quizzes, there's a bunch of these. Great. Gauss's law. We had so much fun with this one. Hopefully you feel more confident with Ampere's law. Gauss's law. You draw a fake Gaussian surface around your object. Which surface do you draw? Depends on the object. If it is a cylinder, you draw a cylinder. If it is a rod slash a cylinder, draw a cylinder. If it's a plane, draw a cylinder. If it's a sphere, draw a sphere. Why does that matter? The left side is E dot dA. The area, the surface area of that object corresponds to the shape that you did. If it's a rod, it's the outside area. If it's the plane, it's the top and the bottom area. If it's a sphere, it's the total outer area. If you're unsure why, check back the previous slides. And this Q enclosed, make sure you can find Q enclosed. This was a challenge on test 1. I gave you all a problem with that where you had multiple objects inside each other. What you did is you found the charge enclosed for one object, you found the charge enclosed for the other object, and you added them, assuming they have the same charge. If they're opposites, minuses and pluses, you still add them. They're just going to cancel out a little bit. So, make sure y'all can, the problem in the last test, useful, that was a sphere, but make sure you can do a line of charge still. Because it's not a guarantee I'm going to give you a sphere. Basically, I'll straight up tell you, the two problems I can hypothetically give you are objects like multiple, like the test where it was like a point charge inside of a sphere, or there was like a sphere inside of a sphere. You can have a rod inside of a rod, a rod inside of a cylinder. You can technically have a bunch of planes. I think practice on those, so there won't be one of those. But make sure you can do that. Make sure you can find charge enclosed, when to use it. Infinite rod, infinite plane, sphere, yada yada. Here's how you do it. Yay. Make sure you can do it. Okay. Oh, look, and there's the rod one. Yay, look, I drew a cylinder. Electric potential. This is another way of looking at things. We talked about fields. We talked about forces. Remember from physics 1, you all learned about gravitational potential energy. This is giving us this idea of energy. Energy is a useful thing. This one still says electric field, and the next slide's going to say potential, hopefully. Yeah, great. You got to build this system. You get energy stored in. Energy is great. It's not a vector. It's so nice. You only care about the endpoints. It's very, very convenient. Make sure you all can do the conservation energy problems with this. If you have two charges near each other, or you have some charge and some potential difference, how fast is it going to go? That was like one of those problems that popped up quite a few times. Know which way charges are going to move. Protons go from high potential to low potential. Electrons go from low potential to high. Notice I said potential, not potential energy. They're both going to lower potential energy, but potential is not potential energy. Don't mix them up. Electric potential and electric potential energy are not the same thing. Electric potential is like height. Electric potential energy is like when you put something at that height. Now it has energy. Right now there's the potential to have energy. Now it has energy. There's something there. That's the difference. Alright, great. Make sure you can find electric potential. That's V. There's 3 names for electric potential. I know it's a pain. I didn't make the rules. I just teach them to you. There is voltage. There is electric potential. There's potential difference. They are all the same thing. Voltage, electric potential, potential difference, all the same thing. How do you know it's not energy? It doesn't have the word energy in it. If it's energy, it has the word energy in it. That's a good rule to follow. All right, great. Make sure you can find it. Electric potential, there it is. It's really about the electric field. Charges make it a potential. It's KQ over R. This looks very similar to electric field. Electric field was R squared. Potential is R. Make sure you're careful on those. It's a really easy mistake to make. All right, problems on it, yay, did some simple electric field. Capacitance, this one was actually pretty simple, hopefully. This capacitance section, a capacitor stores energy, specifically by storing charge on it. You charge it up, we just recently learned that the energy is stored in the field, but yeah, you charge it up, how much energy does a capacitor have? On the formula sheet they give it to you is 1/2 Q times V. Notice that there's a bunch of versions here, they just come from using C equals Q over V and doing some algebra. So if you use C equals Q over V, you can build, all the other ones from it. Capacitance is its ability to store charge. Think about it like balloons. Not all balloons are created equal. Some balloons can store more water in them, given the same amount of pressure that you apply. Another example is like car tires. Different car tires can store different amounts of air based on their size. Different capacitors can store different amounts of charge based on their size. Bigger area, yay, more room. Closer distance, it's easier to store more charge because the plates are closer and they kind of the charges get pulled on there easier.
For all these circuits with like capacitors, why can't they just use extra batteries?
Yeah, it's a good question. For all these circuits using capacitors on these extra batteries, remember they have different purposes. Capacitors can be used for timing circuits. So we did talk about RC circuits, we'll mention that briefly. Capacitors are also, think of it like a car tire versus a pump filling it. A pump filling it, I can add a bunch of air steadily, but I can't add a bunch at one time. If I splash that car tire, it's going to lose all that air really quickly. So capacitors release energy super quickly, but it's gone really quickly then, whereas batteries, it's more of a slow trickle, but it's at least steady. Like you can keep doing it for a long time. Once capacitors are discharged, it's done. You can't keep doing it. All right, make sure you all know series and parallel. This was something as well in the last test that we had challenges with. Series, no junctions between them. Series, no junctions between them. I can go one to the other, there is no option. The World Series games, you cannot go from the first game to the third game. You got to go between, you go one after the other, no options. Parallel means that I can go from like one front door to the other front door and one back door to the other back door. They share the same beginning and they share the same end. I do not care about junctions when it comes to parallel. All I care is that I can drive from one to the other without going through another resistor, capacitor, etc. Make sure y'all can do series and parallel. Capacitors add in a funky way. They add the way you don't expect. Series, they add unpleasantly. Parallel, they add nicely. Resistors do the opposite. Series, parallel, and the definition of current, that's kind of useful to know. V equals IR, you should really know that. Yeah. V equals IR is probably one of the most important equations for you all in this class as far as engineering and computer science is concerned. If you don't remember that equation by the end of this class, it's kind of sad. Mainly because it's so useful. All right, great. That was test one. You know, if any point in this you're like, I don't remember how to do that. Look at problems. That's the ones you need to study. The ones that you don't remember, that's the ones you study. The ones that hurt your brain, those are the ones you need to study. All right, that's test one review. Yay. Test two review. This is kind of, this is fairly recent. But I'll just remind you all, right now I'm just highlighting what you need to remember, the main points. All of it's written down here. The video will also be posted if you're like, he said things, what did he say? The video's there.
If we have time, can you go over combining the giant DC circuit one on your house?
I can do that individually. Yeah, I can do that individually. I'll just kind of know the main things, then if people have questions, I'll stick around. All right, DC circuits. It's more to say series and parallel. There's a few things here. Make sure you can series and parallel still. The rules for series and parallel include capacitors and resistors. The only thing that changes is the math, how to do it. Resistors just add in series, and parallel they do the other things. Make sure y'all can do the loop rule. Make sure y'all can do the junction rule. I think those went fairly smoothly. And RC circuits, make sure you can do discharging and charging. All these things, everything I'm putting on here. When I'm making the test, I'm looking through these things. These are the important things, and so these are the things I'm going to be testing you on. These are the things I need to make sure you understand. All right, net resistance. These two are in parallel. These two are in parallel. So like, for example, this one, how do I know that these are in parallel? It's not because they look like they're in parallel. It's because they share. You can color code these. Remember, that was the technique. I'll do it super quick. I'm going to color code these, and then we'll be able to see which ones are in parallel by identifying which have the same color at the beginning and which ones have the same color at the end. These ones are in parallel, same color beginning and end. These ones are also parallel. I actually made the same mistake last time where I put a different color there. Remember, the color stays the same. When does it change? When you pass a resistor or capacitor. So this circuit turns into this. This one would be R over 2. This one would be R over 3. I did some quick math in my head. You'd actually have to do the math. Don't just like, oh, in parallel, I just divide it by how many there are. And if they're all the same, but if they're not, then... and so this one turns into R over 2 plus R over 3, which this one you have to do least common denominator. So that equals 3R over 6 plus 2R over 6, which equals 5R over 6. Okay. All right. Make sure you can do that. Loop rule, junction rule, we did that last time. They're all posted, yay. Right-hand rules, they still exist. They didn't go anywhere. If they didn't go smoothly for you in the last test, make sure you practice them for this one. They are what they are. Make sure you can do them. Remember that electrons experiencing force in the opposite direction. Do not mix up electrons and protons. There was a question on the last test with electrons and protons. It was an electron moving. I generally on a test underline directions and also what type of charge. I do not want you to miss a problem because you scanned the problem and you didn't read it carefully. If I underline something in a problem, it's probably a detail that's relevant. That sounds obvious, but it's a test-taking skill. I am doing that because I do not want you to miss a problem because of reading comprehension. Sounds silly. I don't want you to miss a problem because you're just reading through it really quickly. So, be careful. Read these things. The real world's not as kind. The real world, they don't always underline things for you. But you got a lot of them trying to teach you, so give you something. All right, moving charge, experience of force. There's the equations. Yay, make sure you can do that. Remember, they go in circles. Make sure you know the equation for that and also be able to predict which way that circle will be. Yay. Make sure you can find the force on things when it varies over stuff. Multiple wires. Make sure you can do an arc, a finite line, and a solenoid. Those are the three examples. You better be able to find the fields to them. If there's multiple of them, combine them together. We did that. Yay. Ampere's law. It's kind of like Gauss's law, but easier. Make sure you can do that. Again, a lot of this is me just saying, here's a topic. It's important. Here's a topic. It's Faraday's law. Remember that it's N, which is the number of loops, times the change in flux with respect to time. If I give you a function, you can actually take the derivative. If I don't give you a function, you would just find the average, i.e. change beginning minus final over the time it takes. You can only do a derivative if I give you a function for it, but there is problems where I give you functions for it. Make sure you know how to do the rotating object one. That showed up in the last test. That is something you all need to know because it's how generators work. Fairly important to our society. Again, I have the perspective that every scientist and engineer should probably know where electricity comes from. It feels fairly important. It feels like something engineers, I feel like that's an easy argument. All right, so make sure you can do that mathematically. Lenz's law, make sure you can do that. Am I getting more or less? Counteractive change, right-hand rule 2. How do you make sure you can do this? Practice. Inductors was the last thing we talked about. They exist. Make sure you can do the equations with them. That's it, y'all. That is me saying every topic that we remember in a very quick way. So at this point, honestly, if you have individual questions, I'll stick around. But that was what I really just wanted to cover today. That was the highlights. Make sure you all give yourself a day to rest at some point, at least a day. I know you got a lot going on. Some of you do have a lot to learn. But it is worth spending a day to rest. Everyone, you need it. Enjoy your all's quote-unquote break. If you can call it as such, depends on your perspective, where you're at.
Happy Thanksgiving.
Yeah, have a good one, y'all.